and then we'll just kind of combine it with this session today. Okay, so this is a recap from the last chapter. Let me change the color. I do like the brighter red. So in general, pH, you can see my screen, right?
Yes.
pH is equal to negative log base 10 of the hydronium ion concentration. Okay, so from the previous chapter, chapter 16, you should have concluded in the many formulas they gave you, pH is equal to negative log base 10 of H3O plus. Okay, so while I'm here, I'm going to tie this into today's lesson. When I was in school and we were learning this, back when I was in school years ago, H plus was pretty much equal to H3O plus. And I have stated this before. So when I was in school, we weren't using the hydronium here. And for me, it was an easier entry point than the hydronium ion. So when I was being taught this in middle school, they taught it as pH equal negative log base 10 of the H plus concentration. I liked this one better than this one, even though they're the same, or they have the same connotation or same meaning, because this is equal that, because I could see how the P stands for negative log base 10. So every time you have, I shouldn't say every time, in this context of the acid base chapter, when you have like say pH, the P stands for negative log base 10 of the letter or the symbol or the formula written in front of it. Okay, so just to illustrate this further, then I'll come back to working out that table. To illustrate this further, let me give you a bunch of P's, right? In the previous chapter, you saw pH, you saw POH. I don't know what other P was seen, but while I'm here, I'm going to go over a bunch of P's. pKa, pKb. What other P is there? pKw. Okay, so what are these equal to as far as their formula? So these stand for a measure of, P has to do with the measure of the hydrogen ion concentration, but these quantities are also equal to other quantities mathematically. So P is equal to negative log base 10 of H plus concentration, like I told you, or negative log base 10 of H3O plus concentration. Okay, so if you're asked to figure out the pH and you're given H3O plus concentration or H plus concentration, plug that number in this formula and you can solve for pH. If you are given OH minus, plug this in here and you can get POH. So if you need an additional visual, this P stands for negative log base 10 of the concentration of the symbol written in front or to the right of P. Okay, so same thing with here. For P, I'll write negative log base 10. And I'll go through all the array, negative log base 10, because P stands for that, negative log base 10. Then when it comes to Ka, I'll write here Ka, Kb, Kb, Kw, Kw. Okay, so P stands for negative log base 10. And so the P goes with H, the P goes with OH, the P goes with Kw, I mean Ka, Kb, and then Kw. So hopefully you can see that. Okay, so I'm trying to summarize this in an overview versus going in the order that the slides show that. So if you're given a table and asked to solve for, in this case, pH and POH, the direct question you want to ask is, if I have pH, am I given H plus or H3O plus? If you are, take that number, take the negative log of that number, and you get your pH. If you're given the OH, sorry, it's supposed to be OH minus, and you take the negative log of that, you get the POH. Kind of like what we did when we last met, which was last week. We did that over here, right? We had the OH minus concentration. Oh, we didn't do that, Max. I skipped over that part. I get it now. Okay, it's coming back to me. Okay, I see. Okay, so this is something that you were supposed to understand from the previous chapter, the implications of P. They stated it's not summarized this way, but one thing I learned in chemistry, that even if I have to be quick to recognize those deja vu moments. Like when I did the pH and I saw the POH, I'm like, wait, these are similar. They all start with the same negative log base 10 of blah, negative log base 10 of blah. Then when I saw the pKa, I'm like, wait a minute, let me guess. Negative log base 10 of Ka. You just said it, and I was like, okay, I'm seeing the trend now. Every time I see P blank something or P blah blah in this context of acid base chapter, that P stands for negative log base 10. Does that make sense? So I'm going to work one out for you. So if in the lab table you were given, I probably wrote this very small. Let me make this bigger. So if you're given a table where you're given the hydrogen ion concentration, and you're asked to find the pH, and say the hydrogen ion concentration is 0.1, what is the pH? Knowing that the pH is equal to negative log base 10 of H plus, just take this number you have here, negative log base 10, plug it in here, 0.1, and then solve for that. Where's my calculator? So I have my calculator right here, which is clear, 0.1. I have to find my log function. My log, press 1 to get the log function, 0.1 in parentheses, and then don't forget the negative here. So I have a negative. From here, I got -1, and so my answer will be 1. So I'll put 1 right here. Does that make sense? Does that answer your question?
Yes, thank you.
Yeah, so essentially they give you what goes here for you to know how to solve this part. Okay? Okay. So that also applies for the P. Let's see. In the case of the OH minus and then the pH, remember the P is a negative log of whatever symbol is written here, right? So if you have OH, you cannot put OH right here. So you may want to use the other formula. Okay, POH, let me erase this part here, equal negative log base 10 of OH minus. But they want pH here, not POH. So you go ahead and solve for the POH first, but that's one step before the pH, right? So it's an indirect path to pH. So for the oh my goodness, I'm on eraser mode. For the POH, do the same thing, negative log. I'm going to plug it in here just because I started. Negative log 1. I should turn the light on. Hold on. I'm struggling to see it. It's dark over here. I don't know. It's those things I do sometimes that make zero sense whatsoever. Okay, so I get 1 here, right? But I can't write the 1 here because pH and POH are not the same thing. They're measuring concentrations of different ions. They're completely different. We can't assume that H plus is always equal to OH minus in a solution. These are only equal if the solution is neutral. It's safer to assume that these are not equal to each other, okay? So we can't just write the 1 here. We actually have to figure out the pH. So we know from the previous chapter, pH plus POH equal 14. So if we know the value of POH as 1, then what is the pH? pH plus 1 equal 14. So let's see, minus 1. We end up with pH equal 14 minus 1, which is what, 13. H here is actually just with a basic pH. In the pH scale goes from to 17. Not really. 7 is when you have a pH of 7 is neutral. That means it's neither acidic. And 7, this is going to be the acidic region, if I can say this correctly. From above 7 to 14 is basic region. So this is basic, and the left side is acidic. And how do we measure acidity? It all boils down to the number of H plus ions. How do we measure basicity? Number of OH ions. The more H plus we have, the more acidic. The more OH minus we have, the more basic. So this is acidity, and this is basicity. Okay. So like at the mental level, the that acid is like, it go to a room where there are flammables in there, they have a sign like picture of or a triangle with a flame, it communicates to the room. Be careful. Things in here they're flammable. In this case, this symbol here indicates acidity. Whatever you're handling is acidic. Here, this is basic. Whatever you're handling is basic. Both acids and base burn, but differently. I mean, from a human point of view, it burns. Okay. Anyway, so I'm gonna be. Does that answer the question then, as far as those two tables are concerned?
Yeah, it does. Thank you.
Okay. So we are picking up where we left off last week. It's hard for me to tell these days, y'all. Bear with me. What days of the week it is when we last met. Every day is yesterday or today, right? Okay, we're now dealing with basic buffer. And as you can see here, once again, it helped for me when I was in junior level chemistry. By junior level chemistry, I'm like, I got this, okay, I got this. And begin to recognize the symbolism of some of these ions, what they indicate, right? When I'm seeing a basic buffer, so before I get into basic buffer, I want to quickly review acidic buffer. In our acidic buffer, one of the telltale signs I had the acidic buffer was the formula, right? My equilibrium formula. I knew it was acidic because, for one, let me try to write this smaller. There were so many symbols. There was a Ka value associated with the equilibrium once the equilibrium was written. So I'm going to write the acetic acid acidic buffer, okay, where the Ka is 1.8 times 10 power negative 5, I think. I think that's the number. So since I'm writing an acidic buffer here, I'll write my acetic acid formula. HC2H3O2. So this is the normal format of the acidic buffer. You have a weak acid, right? That is an aqueous state. To that, you add water. So on the reactant side, this is the expectation you should have. Any weak acid formula added to water. The water is in liquid state. Check. So these are two requirements are done. Weak acid added to water on the reactant side. On the product side, since they said it is acidic, I do have an expectation. What is my expectations? One of these products will be the hydronium ion because remember, acidity is signified by either H plus or H3O plus. So if this buffer is acidic, one of the products has to be written either this way or this way. Since we have water, we're most likely going to see it written this way. Okay, so let's see. On this side here, I'll write H3O plus, which is what I expected for an acidic buffer. So this fulfills my requirement. And then the other side will be the conjugate base of the weak acid, the conjugate base. So everything here except for the H, right? So C2H3O2 minus the conjugate base, also in aqueous state. So these four formulas are expected. Weak acid on the reactant side, water on the reactant side. On the product side, this weak acid becomes that conjugate base as expected, duh. The water becomes the hydronium ion, right? As expected. And then the Ka. So looking at this, I'm like, okay, I can see this is a acidic buffer. Then I move on, and now I'm going to be writing a basic buffer because I wanted us to review acidic buffer before we scaffold, build up on that, and look at basic buffer. So basic buffer is similar to acidic buffer, only this time the focus is everything basic. So we're looking at a basic buffer. Okay, let me see. In a basic buffer, they have. Okay, so I'm going to try to fit the format of the acidic buffer so we can see the difference. I'm not going to start with water. I'll start with ammonia. So for the basic buffer, with the operative word being basic, I'm starting with my weak base. My weak base here is ammonia, AQ, kind of like I had up here, right? Plus my water, water. Also liquid. Equilibrium arrow, equilibrium arrow. Now let's see. Remember Bronsted-Lowry. In Bronsted-Lowry, the weak acid has to give up its H plus to become the conjugate base, right? Essentially this, let me remove all these arrows since I wrote a lot. This has to lose H and positive to become this ion. But since this is a base has to gain H plus. The base does the opposite of the acid. So you see how in this new chapter, we are still relearning and going over what we learned in the previous chapter. So the Bronsted-Lowry base gains H plus to become the conjugate acid. So gaining H plus, remember we covered this before, and remains as is because the number of N didn't change. H increases by 1, and then we get a positive. So now this is our conjugate acid, right? The resulting molecule after the transformation has taken place. This is also AQ. Now here, we cannot have HBO plus. No, no, no. HBO plus goes with the word acid because we have base. Well, is OH minus. So it took me a little while. I don't really remember how long, but one day I was like, wait a minute. Is this what we're doing here? When I have a basic buffer, should I expect an OH on the product side? And she just said, yes, like, isn't that what you were thinking this whole time? I'm like, no, didn't say it. And I have a slow processor. It's like processing really slow. I'm like, why didn't you say this? And since basic goes with OH, and then OHB, not KA, and then this has a number that goes with that. Once I got that, I'm like, oh, okay. Now, when I see a basic buffer or acidic buffer or even an acidic reaction with equilibrium, I have certain expectations. And those expectations help to anchor me in my path to setting up my I-stable, solving complex problems and stuff like that. Okay. So we're learning the new chapter while we're reviewing chapter 16. So there's a KB that goes with this. I don't have it memorized. It should be somewhere here. Or they get to it eventually. Anyway, so what I just wrote right here is this equation. Of course, they wrote it weird. Y'all see, I flipped this to match my first acidic buffer. So to make a basic buffer, you need your weak base. In this case, our weak base is ammonia and the conjugate acid, ammonia chloride. Okay, so you get this combo here, NH3 and NH4Cl. So if you're trying to examine these, how are these two different from each other? To go from the first formula to the second one, you have to add H plus, right? Remember, these two therefore are acid base conjugate pair. These are two formulas that are conjugates of each other. One is an acid, the other one is a base, and the difference is a H plus. The difference in the formula is a H plus, and we practiced how to do that before, right? It's in your homework in a quiz. Make sure you know how to do this. Okay. So we've written our buffer here. And for this part, they show you then how pKa and pKb are related to each other. Remember, I told you what pKa is? P standing for the negative log. They left the base 10 out here because mathematically, I guess the base 10 is implied. And so they leave it out. I remember learning this in math and I asked my teacher, well, why is it left out? Because it just is. I'm like, "Oh, okay, I guess we all just kind of making rules as we go along, right? Okay. So I usually say it's implied. If it's left out, it's understood to be base 10. If it's base 2, it's never left out. They will say it. Okay. But base 10 is left out, is implied. So this is negative log base 10 Ka, negative log base 10 Kb. The bottom line you need to know here, I would say, besides what pKa and pKb stand for, is you need to know pKa plus pKb equal 14. Remember, we also learned that pH plus pOH also equal 14. But these are formulas that you want to have with you because they're useful formulas in this section. We don't get a lot of formulas in chemistry, but when we do, we want to remember them. Okay? So this will help you go from acid base. If the focus is acid, but they want you to get base information from the acid, these two formulas will help you go back and forth. Oops, I spilled some water. Sorry. I'm trying to wipe water from my iPad. I spilled it a little bit. Okay. We are now going to be figuring out the pH of a buffer solution after adding acid or base. So they want us to get the pH again of the buffer. Ooh, remember I said this last week. When you're trying to figure out the pH of a buffer, you have two possibilities. You can use the Henderson-Hasselbalch equation or you can use the ICE table, whatever you're comfortable with. Okay? And then they say here after they've added an acid or base. Oh, that means we have to use, if you're using the Henderson-Hasselbalch equation, you have to use the modified one. Okay? Oh, they say it here in the dialogue. Okay, well, I guess we don't really have much of a choice, do we? Right? They say here, calculate the pH of a buffer solution composed of a weak base and its conjugate acid. Ooh, if the weak base is the part that's weak, that means we're dealing with a basic buffer. Okay? So I'm the kind of learner, when I'm learning, I think my husband doesn't like this very much. I have a lot of questions because he's like, if you just listen to me and you let me get to the end, I'll probably answer your questions. I'm like, well, the way my mind works, if I have a question that's not being answered while he's talking and going on, I'm still obsessed with that question and I fixate on that question. So I'm not even hearing him anymore. And I've told him, like, maybe your mind works that way where you can let go of things you don't get. I fixate on things I don't get. And I need to resolve it before I move on. So my teachers and I from school, we are, let's just say we are at peace now. When I read the term basic buffer, like weak base, I want to know, are we dealing with an acidic buffer or basic buffer? When they say weak base, they mean basic buffer. If they said weak acid, they will be meaning acidic buffer. Okay. Those are the kind of questions I want resolved as I read the question. I don't want to still be trying to figure it out. I'm trying to solve the question. So we're told here, use Henderson-Hasselbalch equation to calculate the pH of a buffer solution that is 0.5 molar ammonia, zero point 0.2 molar NH4Cl. For ammonia, the pKb is 4.75. Okay, here's the thing. Okay, here's the thing. Remember when we had the Henderson-Hasselbalch equation? Okay, I'll call this the HH equation. pH equal pKa plus log base over acid. This equation right here, this equation was written, since it has pKa here, this equation was written for an acid buffer. Okay, from what I remember, this was written, it was derived from an acid buffer. But what you're telling me right now, this is a basic buffer. So the question I would like to ask my teacher right now, which they used to give me that look, can we just use this equation right here? And the answer they will tell me is yes. Even though this was written for an acid buffer, It can be it can be used for a basic buffer, but you have to make some modifications. Okay? Acid buffers have pKa, right? Basic buffers have pKb. Well, we need to resolve that because in this formula here, we don't have a pKb, right? But that's no problem. Don't we have a formula that relates pKa to pKb? Yes, we do. So that's simple. pKa plus pKb equal 14. So if we need to get the pKa from pKb, just say pKa equal 14 minus pKb. Problem solved. And I'll be like, okay, that problem is solved. I know. I must have been a very fun student. That's what I'm saying. But I really wanted to know. I wasn't that kind of person who just took stuff and said, oh, yeah, because you said it, you're grown. So I accepted. Nah. But overall, I was I mean, in my opinion, I was very compliant. I just had to understand. Okay, so we got 4.75 here. They gave us pKb, right? Right? 4.75. So when you plug it in here, we get the pKa. 4.75. Subtract that. Now we get a portion of the equation that we need. 14 minus 4.75. Okay. And by the way, all the skepticism I had, it helped me to really engage with the material and own it. So it wasn't just their chemistry. I owned the material, so I understood, right? Because I was trying to really engage with the material and understand it. So I got the pKa portion. This part of the equation I got. Now, what about the base and the acid? Okay, so here, let's see. What's the base? What's the acid? Base and acid, according to Bronsted-Lowry, is all relative. So let me see if I can zoom out so I can copy these numbers. Give me just a moment. Let me copy. Oh, the font is so tiny. I have NH3 that is equal to point, is it 50? It's hard to see, it's so tiny. And then NH4Cl is equal to 0.20. Okay, now I can zoom in. Okay, so I have this formula here and I have this formula, right? And I have these concentrations for this formula. I need to know which one is base and I need to know which one is acid, right? Now, they labeled this earlier. Ammonia here is the weak base, okay? And this, not the whole formula, just the NH4 plus part is the conjugate acid. Remember, the Cl is the escort, is the father of the bride that just escorts the ammonia to the solution. Once they get in solution, the father of the bride, aka Cl, just parts off, right? So this is a weak base and conjugate acid. So we'll go by these titles here. Weak base is still base, conjugate acid is still acid, so we'll go by that. Okay, I guess it works. I guess it wasn't as complicated as I thought it would be. So pH is equal to pKa, we got that, plus log base over acid. Put this in parentheses. So now we got our base. This would be NH3. We got our acid. This would be NH4 plus, right? So pKa, what was that number? 9.25 plus log in parentheses. Our base is 0.50. Our acid is 0.20. Okay, let's do this. 0.50 divided by 0.20, and I get plus log of 2.5, 9.25 plus. Okay, 2.5, let me get this in my calculator, 1 to the answer, log. Okay, so here, oops, 9.25 plus 0.398. And so when I add these two plus 9.25, I am getting 9.64. Okay. So when you make a buffer with this amount of weak base and this amount of its conjugate acid, and you mix it up together and you read the pH of the solution will read like this. Is this consistent with a basic buffer? Yeah, this buffer is in the basic region. Remember, basic region is greater than 7. How about greater than? Oh my goodness. I can do this, y'all. I can do this. Hold on. I put the pH, right, is greater than 7, right? But less than or equal to 14. That's what I meant to say. So the buffer is somewhere in this region here. That's basic. Okay. So they go through and show you how they work it out right here. The answer is slightly different. Oh, they rounded up. I didn't round up, but yeah. Okay. So you can use that. Now we're moving on to see how effective the buffer is. Okay. Remember here, the chemical has a lab purpose, or you can say a life purpose, but the chemical is not a person. The chemical is a means to an end. The person, the lab scientist, is using the chemical to accomplish a goal. The chemical is being used as a tool. What is the role of a buffer? The role of a buffer, I guess I can write it down here, is to maintain pH of solution. We discussed this before. How does it do it? The buffer has two components. The buffer has either an acid portion, usually a weak acid, and it has a basic portion, usually a conjugate base, and it uses either side of the chemical to neutralize any incoming threats, right? So now we're trying to see how can you know the buffer you made, which is used to maintain the pH of any other solution, is a good buffer. We're told a good buffer should be able to neutralize moderate amounts of added acid or base. If your buffer is not able to do the minimum, it's not a good buffer. You can't brag about being a good buffer designer. You're just not. Okay. However, we're being told there's a limit to how much can be added. When they're saying how much can be added, they mean there's a limit to how much acid or base can be added before the pH changes significantly. Okay, so to paraphrase this, you can ask the question, okay, buffer chemical maintain pH, we get it. But is there a point where the buffer can't maintain the pH anymore? Yes. If you add too much acid or you add, see how they use the word moderate here? Yeah. If you add too much acid or too much base, at some point the buffer is not able to work anymore. Okay. So there's such a thing as a buffering range. The buffering range is the pH range at which that buffer can be effective. So man, I wish we were on campus. I could show you guys this. In our lab storage room, we have different buffers. We have pH equal 1 buffer. We have pH equal 2 buffer. And we have so many buffers. So depending on what level we're trying to maintain our other solution at in the experiment, the protocol, the direction would say, well, go ahead and grab pH 4 buffer. That means they want your reaction to be maintained at a pH that's very close to 4. Okay, so different buffers have different buffering range and range in which they can work. And we're told here the buffering capacity is the amount of acid or base a buffer can neutralize. So the buffer has a buffering range and the buffer has a buffering capacity. Capacity is ability to do the work, which is neutralize, right? So we're told here the effectiveness of a buffer depends on two factors: the relative amounts of acids and bases that you add in the ingredients, and then the concentration of the acid and base you use. The higher the concentration, the better quality buffer you have, right? When you use a lot of acid and base, the buffer will work for a long time. Okay, well, how do we figure out the buffering range? We're told what pH the buffer will work in. A buffer will be most effective when you have a base to acid ratio between zero point 0.1 and 10. So what I want to do with this part here is I just want to go over this conceptually because we don't do much with this so much in the lab that I feel like I should spend a lot of time on this part. But telling you based on this equation right here, we have an effective range of the buffer that is related to its pKa. So when you remember, the buffer is either acidic buffer or a basic buffer. Okay, so let me try to emphasize that part. Now, what they're teaching you is designing. We're not designing a computer program. No, we're designing or we're talking about designing, making a chemical solution. So we're talking about, making ingredients, chemical solution, which is a buffer. So when you try to make a buffer, you have to have a target pH. Okay, target pH of effectiveness, operation, something like that. Target pH of effectiveness. Okay. In other words, you're saying my buffer, once you make your buffer, will maintain a solution at blank pH. This is your target. So you're saying once I make this buffer, I will market my buffer as this is the best buffer ever, and it will work. It will maintain the solution at a pH of, I don't know, 7.4. So if that's your target pH, you have to pick the right ingredients to make a buffer that will maintain a solution at this pH, regardless of what changes take place in that solution. So they're telling you here how to grab the right buffer off the shelf. They tell you first thing is you want to know the pKa of that chemical. Okay, so the first thing you want to write in making a buffer. Remember, if you're making an acidic buffer, you need two ingredients. Two ingredients. Am I spelling this right? Okay, I meant to say ingredients. Okay. Number one, if it's acidic buffer, you need a weak acid. And you need, number two, its conjugate base. Okay. I'm not going to go into specific amounts right now. I'm just giving you the overview. Well, which weak acid do you pick? There's hundreds of them. Which one do you pick? It all boils down to your target pH. So they're saying right here, look at the pKa of the acid. So there's a published list online in your textbook of the Ka that goes with the acid. So say, for example, you're going to pick a weak acid. You can pick hydrofluoric acid, or you can pick, these are the common acids, acetic acid C2H3O2. These are both valid weak acids, right? But you want to pick the one whose Ka or whose pKa is closest to the pH you want. Okay? So they're saying here, pick an acid whose pKa is closest to your target pH. Okay, remember my target pH was bodily pH, so which is going to be pH equals 7.4. If my target pH is 7.4, then so if target pH equals 7.4, comma, pick any acid, and I mean any acid, whose pKa is close to 7.4. It's as simple as that. I mean, they make it simple once you understand what they're saying, right? They make it simple. Well, okay, find the pKa. Okay, but how do you know how close? They give you a range here. So you want, if 7.4 is the pH you want, then your pKa can be plus or minus 1, either above or below that pH. Okay. So say for example, if you have, because that's kind of what they're saying right here, the pH has to be either plus or minus close to the pKa. So let me try to explain this part here. So since our target pH is 7.4, then they say pH is equal to pKa minus 1, or pH equal pKa plus 1. So depending on what you have in your storage room, the following range of pKa's can work. Let's see. If you're trying to find this, we got 7.4 equal pKa. This should be pKa minus 1. So I'm trying to work this out. This says 8.4 pKa, or 7.4 equal pKa plus 1. And here I have pKa equals 6.4. Okay, so that means this is our range right here. So any acid with a pKa between 6.4 and 8.4 can produce a buffer at 7.4. So you see how I worked it out? Okay, it's just telling you. It's okay. So people say chemistry is like cooking, and I usually say that too. It's a little bit more complicated than cooking. Though there are times when I do cook and I do crazy stuff, but I don't use this formula, but I try to manipulate units and stuff. They say grams, I want to use ounces. They say big cup, I have a small spoon, and I'm like, I refuse to buy a big cup, so I have to modify what I want, or what they tell me, to match what I have, so I can use what I have to get the same goal, right? Remember, our goal is to get a pH of 7.4. They're telling you you have this range to pick from, right? And once you have this range to pick from, then you can decide from here what buffer to make. So the goal, bottom line, is pKa of acid must be close to target pH. That's a bottom line we're supposed to learn from all of this. Now, at the freshman level, you guys will not be doing this much in the lab, not so much. But I remember being in a biochem class where we had to make buffers, right? And biochem, it depends on where you take organic chemistry. You may have to do that. I don't know the future. I just know my class and what I teach. But I had to do this in other classes and make a solution with target pH and then work out your math. So yeah. But anyway, that's how that works out. So here I want to talk about the most effective buffer. Once again, this is kind of like um, making solution design. So the most effective buffer will be when your base and acid concentration are close to equal. They don't have to be equal, but close to equal, because you don't want your acid to be, sorry, you don't want your buffer. So the best buffer, I should say here, best buffer has roughly equal, not exactly equal, equal amounts of acid and base. It doesn't have to be the exact amount, but it has to be roughly equal. And not only that, so this is the first thing about the best buffer. Second thing is, best buffer has large amounts of acid and base. Okay? The role of the buffer is to equally neutralize any added acid or any added base. Its ability to neutralize has to do with the amount of chemical and the concentration of the chemical also. So if you have a buffer where there's so much acid, very little base, and then the threat that comes in is a base, it won't be able to work well for long. Okay, but you are an artist of making chemicals. You want to be a good artist. That's your art. You want to make chemicals that you can be proud of, that your boss can be happy with, and then you get a bonus, right? Anyway, so we're teaching you that here. Just a little bit, not so much in Gen Chem. You do a whole lot more in organic to teach you how to do the stuff, y'all know, right? Anyway, I got a whole Breaking Bad. I won't get into all that stuff, but yeah, you gotta know the chemistry to know how to make good chemicals. Okay, this was part of the stuff that was in your lab, and I was really hoping as you read the chapter, you will get, relate this to the lab, the acid base lab. There was a picture that was similar to this in chapter 16 that talked about the acid and the base. But it's saying here, a concentrated buffer can neutralize more added acid or base. So we're kind of saying the same thing over and over again. A concentrated buffer works longer, and then dilute buffer doesn't work as long. It's not really a time issue. It's just the chemicals ran out. So when they ran out, so if the weak acid neutralizes the base, this part is gone. If it neutralizes again, it's gone. And then you're like, empty. And you have to dump the solution out, make some more. But if you have a lot of a concentrated solution, you have to use up all the chemicals first, before it runs out. So when I was thinking about this, even when I think about it right now, I think about a battery. A battery is not a buffer. That's a whole different kind of chemical reaction. But the point of how the battery works, it is the science behind it. Even though it's electrical, the electricity is stemmed from a chemical reaction. So as long as you have a chemical reaction, the battery is working. When the chemical reaction is over, the battery dies, right? So you want to have the chemical reaction going on for a long time so that you can get to use the battery for a long time. In this case, of course, the more the chemical reaction takes place, the more the buffer is working. Okay, so here, a problem with dealing with buffers here. I'm only going to answer the first part of the second part. Which acid would you choose to combine with the sodium salt? Which acid would you choose to combine with the sodium salt? Oh, so we're making an acidic buffer because they said which acid. Acidic buffer. Okay. And I can see that from here. These are all acid, 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 acid. Okay, got it. And they're all pKa, pKa, pKa. Got it. Okay, which acid would you choose to combine with sodium salt to make a solution buffered at pH 4.25? Oh, okay. Remember we talked about this, right? Our target pH that we're trying to maintain constant is 4.25. Okay. So if we try to work backward, there's only a certain range of acids which can actually be converted or made into a buffer that will work for this. They said the range was +1 to this number and -1 to this number, right? The pKa was +1 -1, something like that. I've forgotten how they wrote it, but I know what they mean. Okay, +1 -1. So the lowest pKa range that will work is -1 of this number, so that will be negative, 4.25 -1, 3.25. The highest pKa that will work will be 5.25, right? So yeah, essentially this is the range. So anything between 3.25 all the way to 5.25, according to what was said above, will work. So if the pKa is this low or the pKa is this high, somewhere in there it will work. So let's eliminate the ones that don't make the cut. Doesn't make the cut, doesn't make. So out, out, doesn't make the cut. These are out of range, right? So only two make the cut. So if it's two that make the cut, which is the best? I mean, from what I understood here, I think I wrote it out in the notes, right? Oh, pKa of acid must be close to target pH. Oh, so I just need to find the closest, right? Okay. That's why even when I'm reading right now as an adult, I like to summarize what is the takeaway lesson because I don't like to reread a whole paragraph with a lot of words and no pictures. When I have to read stuff, I'm like, oh my goodness, I have to read that whole. How many pages am I reading? Then when I read, I like to write a summary. So if I want to go back and get the gist of what I just read, I just read the summary I wrote. I know, I know. You're probably thinking I'm lazy. I'm just being honest, y'all. Okay, our target pH is 4.25, which is the closest. This one, right? These two are valid. This is valid. This is valid. But this is the closest, right? And so even though both are valid, that's the closest to our target. So we picked formic acid. What do they say? Oh yeah, there. Sorry, let me highlight. The best choice is formic acid because the pKa lies closest to the desired pH. Right. But for us to make sure we get the solution maintained at that exact pH, it matters what the ratio of the acid and the base is. And so that's how they work it out to say that this must be the ratio. I won't go into all that stuff. Now I want to go to titration. Okay, we just talked about acids and bases and how we can combine those two to make a buffer and what the role of the buffer is. The buffer will keep the solution pH constant, okay? And when people are doing chemistry in life system, biological systems, it's important to create a buffer to maintain the biological system at biological pH, which is 7.4, depending on the body part, right? Okay, titration. Titration in the lab is a method by which there's a lot of strategy in chemistry, right? A lot of problem solving strategy. So 1412 is definitely upper level than 1411, right? We are learning skills that are marketable not only in lab, but they are marketable in helping us be able to make solutions, right? So marketable in that way. So as we look at titration, we're seeing here titration is a means to an end. A lot of things in chemistry that we learn at an upper level is a means to an end. What is the end goal here? The end goal is determine solution. Oh, concentration. I was going to say solution concentration, but I'll say it this way. Concentration of unknown solution. Okay. So when I was in middle school, we started titrating slowly in middle school, just kind of, playing around, doing simple titrations. Then we got to high school, we started doing more hardcore titrations, right? And I knew when we did it, kind of like a dance move, when you get to this move, this is what comes next, or, music move, this is what comes next. But I never really knew the why. We just did it. I just knew this comes after that. Then later on, I realized, oh, if you want to know, if somebody asks you how concentrated is this liquid and there is no number anywhere, and you're trying to figure out, is this a very dilute liquid or very concentrated, but you need the numerical value, titrate. Titration is a way in which scientists get the concentration of an unknown solution. Or even if the solution is known, we want to know what its concentration is. You titrate, okay? So now we're looking at acid-base titration. In an acid-base titration, a solution of unknown concentration, which is called the titrant, can slowly be added to a solution of known concentrations. They're telling you what the goal is, right? So let me try to summarize that over here. And then how it's accomplished. So goal, determine concentration of solution. Method. Now, let me tell you what will be a very, very easy method. A very, very easy method will be if you had a simple machine like a scale, and then you pour your solution in there, and then the machine just said, oh, this solution is 0.001 molar concentration. We don't have one that tells you the concentration directly, not like that. Okay. So there's more than one way to figure out the concentration of a solution Right now, I am talking about titration. And then later on, when it's relevant, I'll talk about a machine that we have in the lab that will give you the concentration of a solution. Okay. But the method here is use another solution, not the one that you have questions about, of known concentration. So you're using the solution of known concentration to find the solution of unknown concentration. So it's like, okay, if you want to find the concentration of a base that's not known, use an acid whose concentration is known to find the concentration of the base. Okay? Okay, so they say here can be added slowly to a solution of known concentration from a burette. Oh, and then here, this is a method. Device used is called burette. I think I spelled this correctly. A burette looks like burette. I'm trying to describe it. I'm like, it's hard to describe. It's a long, thin, hollow tube with a stopper at the end, and it's graduated. Usually it goes up. The ones that I have used go up to like 50 milliliters. So it's really long. It's a long tube, hollow tube, 50 milliliters. So it's like it continues all the way up. I feel like it's half my height. And as a petite person, as they call me, petite, sometimes I had to stand on the stool just to be able to view uh the burette at the top, or even to add liquid to the burette because it's really really high, it's tall. Okay, you add either acid or base to the burette. You have the stopper here, and the stopper helps to add solutions dropwise. So we're trying to add a controlled amount of solution, either acid or base, to the container in the bottom until we get to quote unquote the end of the reaction. So that's where the burette comes in. Okay. So our goal, determine concentration of solution. Our method, we use another solution with known concentration. Device use burette. And burette adds a solution drop by drop. Such a beautiful process, y'all, until the reaction is over. Okay? So, how do we know the reaction is over? When the reaction is complete, we have reached equivalence point. So now we're learning terminology. You probably learned this in 1411, but this is a review. Equivalence point. Equivalence is another word for equal. So what is equal? Since we're dealing with an acid-base titration, equivalence point is where the moles or the amount of H3O plus equal the amount of OH minus. So titrant, which is a solution in burette, I think this one R, is added drop by drop until until reaction is over. Until reaction is over. Okay? Here's the issue. Most acids and bases, which you're going to be adding to each other, have no color. They're colorless. We can't say they're white because they're colorless, but they're colorless. So acids and bases are colorless. Okay, that's a fact. So if they're both colorless, how do we know we've added enough acid or base to the other solution and that the reaction is over? So we use an indicator, indicator to, without being funny, indicate, I know I just used the word, indicate the end of reaction. So what they're trying to say is, listen, you're adding two colorless clear liquids to each other. How do you know you've added enough? You're sitting there in the lab pouring, 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 pouring. How do you know you've added enough? And when you're working with this in lab, it does help many times if you do it wrong, because people will be adding and they'll be like, Professor, this is my second or third burette full. And then they're running out of solution. And then I just kind of lean over and be like, okay, did you add the indicator? What indicator? I'm like, the one that tells you when to stop. Oh, I forgot. We laugh about it. And then I'm like, okay, start over. What? I'm like, yeah, you need to add the indicator because you have two clear liquids, colorless clear liquids that you're adding, and you don't know when to stop. And I don't know when to stop. I can't tell either. It's not about knowledge or lack of knowledge. I can't see any change. So the indicator is that chemical that will change color so that the reaction stops, so that you know the reaction will stop whether you know it stopped or not, right? So it's kind of like a traffic light. You know, the traffic light tells you to slow down, and by the way, yellow is slow down. I know sometimes when you're in a hurry, yellow is like flooring, and you're like, woo, past this traffic light. But no, yellow is prepared to stop, whatever it is in the book. I don't know. I don't even know anymore. And then red means stop, right? And then green means go. So those lights indicate to you what to do at an intersection. So the indicator here indicates to you when the reaction is over, right? So you don't want to forget to put that in there. And the indicator indicates the endpoint of the reaction. We're told here in the endpoint, the pH will change, and therefore the color of the indicator changes, okay? And so the endpoint is also the equivalence point. So I'm going to point that out. Ha. Okay, and point is also equivalence point. Okay, so here's what I'm talking about, right? In this situation here, in the Erlenmeyer flask, we started off with the acid. How do I know this is the acid? Because it says H plus, and H plus stands for acid. So in my flask, I have a specific amount of acids. Now, based on the assumption here, let's say we have 5 amounts of acid molecule. Okay, so I want to point out at the end point of the reaction, when the color changes, amount of H plus equal amount of OH minus. Okay, that's when the reaction ends. So where was I? So now all I have is H plus in my flask. And then I'm going to add OH minus. So you can see here, I have 5 H pluses, and I have 1, 2, 3, 4, 5 OH minuses, and I'm going to be adding them, which is called titration, because you're adding it step by step. It's a step by step, drop by drop adding. Okay, so you add drop by drop. You can see your drops here. As you're adding it, the H plus is neutralized by the OH minus, and vice versa. They're reacting with each other to form water. So you can see here, this is the OH minus combining with the H plus. 2 of the OH minuses have reacted. How do I know? They made water. H plus and OH minus, when they react, they make water. Over here we have the same thing. Okay, this stopper once again helps the scientists control how much drops are added at one point. Okay, so this is the end of the reaction. The end of the reaction is also the equivalence point. So in the lab, we visually see a pink color. Even though in the picture here it shows you a fuchsia pink color, what we really want is this color here, a hue of pink, a blush of pink. If you know what a blush is, that's what I'm talking about. This is actually, this picture here is way, way past the equivalence point. Let me tell y'all a story of my past, okay? Not the full story. Y'all, we don't have enough time. In high school, we did the GCSE curriculum in my high school. This is the British curriculum, okay? One of the learning goals was titration. So we had an exam that where you had to show your ability to titrate and figure out the molarity. Okay, So man, I've been titrating. Now I get nervous. I have test anxiety and all that stuff, right? When you're titrating, man, you need to be calm because if you're nervous and you're trying to turn this, you turn it, and then all this liquid, and you mean to close, and then you open, and all this liquid comes out here. We were doing a mock exam. So the mock exam is like that practice exam, but it does affect your points, right? It's a practice exam preparing you for the final exam, which is the cumulative final, okay? And it's like a final over 2 years worth of content. So I'm nervous like crazy. And I'm like, oh, there's so much writing on this. Oh, and all that stuff made me so anxious. My teacher was going to be coming around to judge my solution. So you can't fake it. I mean, you can't. Like, once you make the solution, the teacher's standing there watching you titrate. And so he's there with a notebook. I feel so judged. I am so anxious. I was trying to get just half a drop, y'all, half a drop, because I was so close right here. I was trying to get a half a drop. I was so nervous, like, and then the whole thing poured, not the whole thing, but just enough to get this look right here. He just saw that and he put an F. Well, lab was graded separately from lecture, but in the end, you had a combined grade. I got an F in lab. I have not forgotten it, y'all. I just feel that like I'm like in tears. Just one drop. I was trying to get half a drop, y'all, and I got so nervous. I poured because anyway, I have not forgotten this. So I'm always telling y'all this is not a gold color because I just have these wounds from the past. So I ended up getting a D overall in that grade because lab was like 50% and the lecture was at 50%, and I just straight up got a. He just stood there. I knew what was up. He walked away like, and I'm like, but sir, you know I can do better. I just was under so much stress. No, I got a D. I got a D. Lecture helped me a lot. Lecture helped. But anyway, I'm sorry. I just had to go back. Yeah, this color. This is not our target color. Our target color is blush pink. So I have never forgotten. Our target color is blush pink, not fuchsia. Fuchsia will get you an F. They only made this fuchsia because they want to take a picture and they want you to be able to see it, and it's harder to see blush pink in the picture. So yeah. I'm sorry, y'all. This just took me back. I'm not really crying. I'm just trying to be dramatic. But yeah. So at the equivalence point, and I still majored in chemistry when I got to college because I've been through it. You know what I'm saying? I've been through it. And I'm like, man, I struggle with this class. I finally know how to titrate. I'm going to major in that. No, for the final exam, I did well. I did well. Okay. My teacher was proud of me. Oh, the past. Equivalence point, we had moles. So the amount of OH minus and the H plus are in moles. Moles of H plus equal moles of OH minus. Yeah, I got a lot of stories, y'all, in chemistry, too many to tell. Okay, and this is where we stop. No, not in the lecture. This is where we stop in our titration. It's over. So let's see. The other thing you want to know about titration curves. So I just, for this part here, I just go over generalities. We talked about this before, right? Now I kind of, oh yeah, in the past chapter, you talked about neutral salt, acidic salt, and basic salt. Let me see if I can remember that because it's been a while since I've looked at that. Okay, so depending on your combination, oh, I put this in the wrong place. Depending on your combination of what you're titrating with what. And once again, since you guys are just introduced to this, I try to keep it simple, right? Depending on the combination of your acid and base, the end point may have one of the following salts formed. Okay, our endpoint. Of course, the context here is titration, right? So once you get to the endpoint, one of the following salts may be formed. So you want to be able, in looking at your salt, work backwards. So from the previous chapter, from chapter 16, we learned that to get a neutral salt, okay, so remember chapter 16, I equated salt to children. I know this is very unconventional, but this is what helped me to quickly grasp the information, quickly recall the information, and then it gave me time to understand it. Okay, the neutral salt. So the neutral salt is the offspring. So what are the characteristic parents that produce neutral salt? Strong acid plus strong base usually produce neutral salt. Okay, what does that mean? That means if at equivalence points you have a neutral salt and the pH of your equivalence point is 7, you can work backwards and say, that means the titration. So I'm going to write here titration, titration of a strong acid versus strong base will produce a neutral solution, aka salt, with pH equal 7. Okay, we can expect that because we know neutral salt babies are made from strong acid and strong base. Now, they're not really baby, but you know what I mean, right? Strong acid, strong base make up neutral salt. Okay, what else did we learn in chapter 16? Chapter 16, we learned that if you're going to have an acidic salt, the strong parent was the acid. Acidic salts, these are made when you have a strong acid, the strong parent, plus a weak base reacting. So once again, how do I survive this? I survive this by thinking about, you know, once again, disclaimer, I don't hate biology. Biology was my second major in my undergrad, so it wasn't, yeah, I ended up with a double major. Anyway, but biology is, to me, is easier to understand because there's not a lot of people say it's a human body. That's not the reason why it's easier to understand. It's I'm trying to be very careful in what I say about biology. There's not a lot of math required. It's not the math that makes it difficult, but it's not a lot of math required to understand the concepts, right? So to me, yes, I do agree. Biology is easier to understand. I also, it's my opinion, it's also very easy to forget, right? Anyway, genetics in biology tells us the parent that has the more dominant, stronger gene tends to influence the kid, right? So I use the understanding in this concept here. That's why I call these the parents. If a strong acid is stronger than the weak base and they got married, then the children will be, since acids and base make salts, then the children will take more after the mother, who is a strong acid. It would be acidic salt. Okay? And then, of course, if the contrary happens and you have, oh, okay, my bad, it disappeared. This would be acidic salt. I can't spell salt. Okay? To make basic salt, we now have weak acid plus strong base, and these together give a nice little offspring that's a basic salt. Okay? So how does it apply to titration? Here we have titration. So in acidic salt, here we see an endpoint with a pH in the acidic region, which is less than 7. So it's consistent with an acidic salt. Over here, for basic salt, we see an endpoint with a pH greater than 7. because we're trying to get in a basic salt. Basic is bigger than 7, right? Oh, I should write this way. Okay? So you can judge the parents that were used in the titration by knowing the offspring. Yeah. Guys, I have so many stories, but I can't go on those tangents, right? I need to focus. Okay, I really am going to focus. Okay. So let me give you guys a little clues in helping you remember how to judge a strong base and a strong acid as we're going to be doing next. Okay. So I'm going to give you some, they say here generalities. I'm going to give you some generalities to the generalities. So in general, that means there are exceptions, right? In general, from pH of 0 to 2 will be classified as strong acid. So let's say pH of 0 to 2 is considered a strong acid. And then pH of 2 to 4. It's general. This is like that's a disclaimer here. In general, in general. 2 to 4 is a weak acid. So in that region right there, weak acid. And then pH of 10 to 12 is a weak base. And then pH of 12 to 14 is a strong base. Okay? The closer we are to 14, we see a strong base, a chemical behaving more basic. Close to 0, we see very strong acid, a chemical behaving very acidic. Okay? But ultimately, it's all relative, right? When we're reading the graph, we read from left to right. You can't see me. I'm lifting my arm saying left to right. Okay. So even if you're not given the title of the graph, you want to be able to know what is titrating what. Okay. So beyond the equivalence point, the solution in the burette is in excess. So the pH approaches the solution's pH. Okay. So here, for the most part, in the books, this is what we're learning in this book here. They'll tell you the volume of the solution in, oh, this is only what's being added, my bad. But what is being read up here is what's in the burette. So I want you to understand this. You have a burette. Burette is that or conical flask, depending on what country you're in. Burette is what they call it in America. In UK and other countries, it's called a conical flask. I had to relearn all these names in different ways. Okay, this is our burette. The pH meter is reading whatever is in here. Okay. So since we are adding base, at first, all we have here is acid. So how do I know what we have here is acid in the beginning? I just look at the data that this machine is producing. What numbers are we getting? Okay. Let's read this chart. Here, in the beginning, before you add any base, it says 1. It starts with a pH of 1. Then it reads a little bit above 1. Let's say 1.1. Then 1.5. Then we get the idea. pH of 1, this is acidic pH. That means in the beginning, when the reaction hasn't yet started, what you have in your flask is an acid. Then you're adding a base to the acid. You see the y-axis is pH, so you're reading the pH as time goes by. Since the pH of the solution in the flask was 1, what was that range I told you again? If it's 1, it is strong acid. Hold on, back here. If it is 1, it is strong acid. Oh, yeah, so they start here with strong acid. This is a label that goes with what's in the flask first, right? And hold on a second. And then this point right here is the equivalence point or the end point. Okay, so let me zoom this in and try to can I do this? Oh, I did it. Okay, what is this point here? If you look at this point here, they tell you this is the end point, also called the equivalence point. What is a pH 7? pH 7 is neutral pH. This is a salt that's pH of 7. That means strong acid and strong base, which this endpoint confirms the title, right? But all I've confirmed right now is the strong acid part. So you keep adding base, keep adding base. When the reaction is over, at the end, when you've emptied the whole flask, not the LMI flask, sorry, the burette flask holds about 50 milliliters. So you've dumped everything in there. We're at this point. The end, like the end, as in you're done, you're about to clean up and go home or go somewhere. What is our pH? At the end, not the equivalence point. Like you're done, about to clean up. What's our pH? Let's see. Our pH is about, let's say, 12.7. What is 12.7 range? Let's go back up here. The little scale I gave you, 12.7, somewhere in here. Strong base. So strong base. So I confirmed strong acid versus strong base. I used the beginning part to figure out what it was. Strong acid. I used the endpoint to figure out it was strong base. I used the middle point to confirm strong acid plus strong base makes that kind of middle point. Okay, so hopefully you see that. And that's how you read that. We're going to be doing some math. Since I'm towards the end of the lecture, I don't really want to do that math right now. I want to go ahead and move to, I'll do that math. So I need to write myself a feature note because y'all know how I am. Let me be polite to myself. Okay. Please complete on Thursday. Okay. And then let's see. Yeah, I want to go through the titration curves as I'm going through the remaining time. Okay. Oh, this is the same thing. This is still strong acid with a pH range. This is still strong base. What's the difference? There's no difference here. Strong acid versus strong base. Okay, so this part is done. Okay, here. I see the title, but I'm trying to confirm it, right? Our starting pH starts between 10 and 12. 10 and 12 was weak base. Weak base. Then it ends with strong acid. So weak base versus strong acid. You see how it confirms that? Okay. Weak base, the base is weak. Strong acid, the acid is strong. So the equivalence point should have an a salt that matches the strong parent. So it should be acidic salt, right? So let's check equivalence point. Acidic salt will have a pH in the acidic region less than 7. Okay, we're going. Let's see, where's the equivalence point? Right here. Our equivalence point corresponds with a, yeah, equivalence point between 4 and 5. This is, yeah, acidic salt. Definitely acidic salt. That's our equivalence point. Okay, let's look over here. Once again, this one here, weak acid. This one here, strong base. Oh, okay, weak acid, strong base. Equivalence point. If we have two parents and the stronger one and the base, equivalence point should be basic salt, right? Because the base is a strong one. And so over here, I go over here. Yeah, confirmation. The salt is basic. How do I know the pH is 8? Okay. And then now we're looking over here, titration of polyprotic acid, right? I want to mention this part 2 here. I'm trying to see, monitoring this. Okay, this shows you the different stages. Oh, okay. Okay, KSP is not too bad. We'll do KSP on Thursday, and that will pretty much wrap up this chapter, and then we'll continue the next chapter. Okay, just trying to remember that I get to cover enough. Where was I? I kind of talked about the pH. Okay, here. So I want to talk about this graph here. This graph is produced by titrating a polyprotic acid. What is polyprotic? Poly means many, and the product means protons, and the protons they're referring to here is H plus. So this scenario is like, say, where do I write? H, let's see, 1, 2, H2SO4, H2SO3, any acid with an H2, H2S, just anything with two H's. Not anything, sorry. It has to be an acid with two hydrogens. So how do I know its two hydrogens from this picture. Apparently, we're seeing here the number of equivalence points equal the number of ionizable protons. Okay, what did I just say? What I'm saying is, if you can find all the possible equivalent points in the graph, that equals the number of hydrogens that can be dropped off from the acid formula in solution to generate those H pluses. Remember, H plus is the acid molecules, right? Or H3O plus. To make these, you need H pluses from the formula. So this H2SO4, it has two H's it can release. This H2SO3 has two H's it can release. H2S, once again, has two H's it can release. So if you have a chemical formula that has the ability, they're all diprotic, right? So I showed you the formula. Now in the graph, how can we tell? So going back to math terminology, which this one I actually know, surprisingly enough. You see how the graph goes from this way, and then it goes to this way. So I'm going to use a different color so you can see. Let me go with this color here. It's like it starts over again, and then it looks like it starts over again, like that. So every time you have that switch, right, this is called the inflection point. Every time you have that inflection point, you have an equivalence point. This one here. So we have two equivalence points, right? So just to illustrate this point further, let me add a page here. So if you're still not seeing it, let me show you how the monoprotic acid looks monoprotic. And I'll give you an example. HCl, the formula. You have your y-axis versus your x-axis. Y-axis is pH. X-axis is volume of OH, base added. So I'm going to give you a generic curve, right? The pH curve, like this. Okay. So what I drew here is pH curve of HCl, or should I say, yeah, monoprotic acid. Oh, I can do this. Monoprotic acid versus base. Okay. So you got that versus that. And then here we have one equivalence point, because the monoprotic acid only has one ionizable hydrogen. That's it. Okay, next one. Diprotic acid versus base. What do we expect here? This is diproduct. So for example, H2SO4. How will this be different? Okay, I'm going to draw my graph so we can see the difference. Let me add another page. Okay, we got two hydrogens to remove right now. Once again, this is pH versus volume of sodium. I should just say hydroxide. Let me be consistent. My brain is so random, doesn't like to be consistent. Added. Okay, there, added. Okay, so this is my first curve. This is my second curve. Okay, so you can see first inflection point, second inflection point. These are equivalent point 1, equivalent point 2. Okay, this is how a diprotic acid versus base looks like. Let's go triprotic. Can we do that? Yes, of course we can. Triprotic acid versus base. Do we have quadroprotic? No, guys, no, we don't. We don't mess with that, but it's implied theoretically, right? It's implied. Okay, so we're gonna do pH versus base added. Do I have enough space? Let me kind of drop this a little bit. pH. Because I need room, right? So pH versus amount of OH minus added. Okay, so I gotta do 3 curves. 1, 2. Ooh, I was doing so good. 3. 1 inflection point, second inflection point, third inflection point. And there we have equivalent point 1, equivalent point 2, equivalent point 3. There. Equivalent point 1, equivalent point 2, equivalent point 3. Okay? So when I zoom out, you can see the difference. The more the ionizable, oh, I didn't give an example, my bad. It's hard to be consistent. H3PO4, how about that? So 3 hydrogens here, 3 ionizable hydrogens. You see that, right? 1, 2, 3. Okay. I've talked about the indicator, the endpoint, equivalence point. And so what I'm going to do right here to prevent me from getting caught up in these slides, I'm going to delete this page. Yeah, you see me do this, delete this page. Okay, so when I come back, I know to start with this page. Okay, so I said start here, and then I'll say here, continue here. Okay, so I'll go over the math, which I skipped over. I don't know what slide number this is. 58. I need to write myself a note so I don't forget. Slide 58 first. Okay, this is for me to go over this part first and then come here. Okay. And then as we complete this chapter here, hopefully, yeah, we'll be caught up. I just want to make sure we're not too far behind, because I feel like no matter what I do, we end up far behind. But yeah, I want to go over the math part as the first thing we do, and then finish up this chapter. Actually, let me see if I can go ahead and move. This is just me dialoguing now. Hold on a second. Let me see if I can move the math part to the end. That might make it a lot easier for me than when I come back. Okay. Yeah, as I'm thinking about it, I'm like, you know what? Since you guys get to watch this at home and watch it at your own pace, let me actually go ahead and finish this part here. I think it'll make it a lot easier for me. I was gonna do this on Thursday. Let me finish this because I really hate being so behind, right? So we're not super behind. Okay, I'll go ahead and start here and just get this part done, the math part done, because I'm doing so much just to try to do this on Thursday. Okay, we're gonna work this, and this is the last thing for sure. This is the last thing today. We're trying to solve a titration problem between a strong acid and a strong base. So we have a 50 milliliter sample of 0.2 molar sodium hydroxide that is titrated with 0.20 molar nitric acid. Calculate the pH. They want us to figure out the pH after adding 30 milliliters of nitric acid. Okay, so as we're solving this problem here, I'm going to walk you through what they do real quick. They figure out the amount of OH, because at the basic level, even though we're looking at nitric acid reacting with sodium hydroxide, we're really looking at H plus reacting with OH minus. This is a net ionic equation. Remember the acid-base problem I asked you guys? Write the net ionic equation, and you probably were wondering, why is she taking us back to 1411? It's to kind of show you that when we're dealing with acid-base reactions, we're really dealing with H plus OH minus reactions. Okay, so H plus is reacting with OH minus, right? So we're trying to figure out how much OH minus we have versus how much H plus we have in this structure right here. And so we can see what is left over and what's reacting. So we're going to be doing that. Let me go ahead and start this page right here. Okay, so I'm going to write my equation out. They said we are reacting, let's see what was given first. Sodium hydroxide. Sodium, let me write it a little smaller. Sodium hydroxide plus nitric acid. These are both aqueous. And we get sodium nitrate, aqueous also because all sodium compounds are aqueous plus H2O, which this would be a liquid. Okay. Aqueous is a dissolved ionic compound in water. Okay. So remember, sodium is technically H minus. Nitric acid is technically H plus because H plus represents the acid, the OH minus represents the base. Okay. Then they give us concentration. So let's see. We're given a volume of 50 milliliters, and the sample here is 0.200 molar. And here we're given a concentration of 0.200 molar nitric acid. So the reason why I paused real quick is because the scenario is actually very interesting, right? So I'm trying to think of the simplest way to approach this. How do I want to approach this? The way they approach it first is by reacting the moles, okay? And then towards the end, they take the moles and convert it to concentration. So let me try to do it that way. Let me stick with the way they're doing it because there's so many different ways to approach this. So I want to write this as a caveat, yeah, before I start doing all the stuff. Let me see if I can lower this. Is when chemicals react, it's actually moles that react. Remember the ice table where we're writing moles, okay? When we in the previous ice tables, amounts were written. So if you were paying attention, and I hope you were, in big M, okay? So I'm going to try to justify to you why that was okay. That was okay. That's my argument. It was acceptable because volume was, oh, how do I drop this even further? Assumed to be 1 liter. Let's look at our volume here. Our volume is not 1 liter. Okay? It's not 1 liter. So in order for us to work with this, we have to try to figure out the moles in liters. Okay? And as you can see that they convert that here. So we have to figure out our concentration in liters. So to determine our amounts in one, I'm writing the word one, in 1 liter. That's what we're going to be doing. Let's see, where am I? Oh, we figure out the moles in 1 liter. So here, I will start with sodium hydroxide. What were we told? The amount of sodium hydroxide was 0.200 molar, but it was 50 milliliters. So we have 50 point, this is 50, come on, 50.0 milliliter of, and the molarity is 0.200, 0.200 molar. Okay, so this amount here is not in liters. You can see that, right? It's not in liters. So we have to figure out the actual amount in liters. We can go ahead and use the molarity formula. Molarity equal number of moles of sodium hydroxide over liters of solution. Okay. Right now, we're dealing with sodium hydroxide before we mix it with nitric acid. Okay, what is my, so I have this number, I have the well, I don't have the liter of solution yet. I can convert this to liters of solution. I need to convert that. So how do I do that? On this side, 50.0 milliliter. When I convert this into liters divided by 1000 milliliter becomes 50 divided by 1000. So I end up here with 0.05 liters. Okay, so my molarity is 0.200 molar. Moles of sodium hydroxide, I'm trying to figure that out. Okay, liters of solution, 0.05 liters. When I multiply this times 0.2, I end up with 0.01, like they have right here. Okay, so my moles of sodium hydroxide is 0.01 moles. Okay, so you may be wondering, well, why are you converting to moles when we didn't convert to moles before? We didn't want to overwhelm you by converting molarity into moles because it wouldn't have made a difference before. Before, our volume was 1 liter. So if you're wondering before why we didn't do this, our volume was 1 liter. And so to get the moles, you pretty much take molarity times volume. And if the molarity was 0.1 molar times the volume of 1 liter, we essentially got the same number in moles. So just in case you're wondering, wait a minute, not I smell, but I noticed something different, right? I was about to say I smell a rat. It's not that serious, but you know what I'm saying? Like, why are you switching things right now? I'm technically not switching things. We didn't say too much back then because we didn't want you to check out, right? But now we're saying the situation requires us to use moles because we don't have 1 liter. If we did have 1 liter, we would use molarity. Okay, so if you're wondering why, okay, there. So this is the moles of sodium hydroxide. So the amounts that are reacting now are going to be molar amounts versus molarity amounts. It's still amounts, just a different way to get to the end. Okay, so I got this. Now I need to know in moles how much of the nitric acid I have. Oh, they gave me a volume right here. Okay, and they gave me a molarity. I'll do the same thing. Okay, so I need to find in moles. I'm still trying to determine the amounts in 1 liter, right? And I do all that stuff. Okay, so amount of nitric acid. Okay, so the amount of nitric acid. Oh, okay, I have the amount. Was it 30 milliliter? 0.2? Yeah, okay. 30.0 milliliter of 0.2 molar nitric acid. Okay, so for nitric acid, just like before, I do molarity equal number of moles of nitric acid over volume of solution, which is of course nitric acid. I'm trying to figure all this before we even mix it up. Okay. And then what do we get? Number of moles of nitric acid before we even mix this up. So let me molarity 0.20 molar times, oh, I have to convert this to liters. I almost forgot 30.0 milliliters. Can't forget because the units won't work out. And this is 1,000 milliliters down here. Then I have 1 liter up here. Take this divided by that. So I have 30 times 1 divided by 1,000. So I have 0.03 liters. So from here, I get 0.03 liters. Okay. So when I multiply these two times 0.2, oh, it's supposed to be 0.2. Okay. I end up with 0.006. Hold on a second. 0.03 times 0.2. Okay. moles of nitric acid. Okay, so I got moles of nitric acid. Now I can go ahead and write my ice table. I had this here. Let me go ahead and copy this here, and I'll use that to make my ice table because I don't want to write that again from scratch. So ice tables are predominantly written for, oh, what did I do? They're predominantly written for weak acid equilibriums and stuff, but you can use it in other areas too. And I'm about to use it here so you can see how it works out. I want to see my initial amount, my change, and then the amount I have in the end. This time, E doesn't stand for equilibrium. E stands for in the end or left over. Okay? Okay, in the beginning, I can see the amounts I have. I have 0.01 molar of base, and then I have 0.006 molar of nitric acid. So I just figured the amount in moles, right? I told you this time we're using amount in moles. So I'm going to write here 0.006 moles versus molar. Remember, I told you why we can't do molar because our volume is not 1 liter. Okay, and 0.01 moles, 0.01 moles. So I finally got my initial amounts. Now these have not mixed yet to make products. So I put 0 here and I put 0 here. And now they have to react. Is this equation balanced? Yes. And this reaction is going to react according to stoichiometry. Remember how we did before, minus x for the reactants, plus x for the products, right? Okay, so which of these two controls which one reacts? Uh, since we have a limiting reagent scenario, we don't have equal amounts of both reactants. The lesser amount, the one that's lesser, will run out first. So we'll use all of this, 0.006 moles. This will completely react. And then same amount here will react. So this will be our x, 0.006 moles. On the product side, how much gets made? Same amount plus 0.006. So this is going to be kind of like our change, right, in terms of x, plus 0.006 moles. At the end versus equilibrium, you see how that plays out? We have 0.006 moles, 0.006 moles, right there. But does anybody care how much water got made? No. Does anybody care how much salt got made? No. What we care is which one of these is present in excess. As you can see, once we add 30 milliliters of nitric acid, this runs out completely. The nitric acid completely gets consumed, annihilated by the base. But we still have some base left over. Let me do some math here. We got 0.01 minus 0.006. We have some base left over. We have 0.004 moles of base. Okay? So, yeah, I'm still answering the first question. They told you find the pH of the solution after you add 30 milliliters of nitric acid. Well, here's what happens after adding 30 milliliter of nitric acid. I'll own it. I have 0.004 moles of sodium hydroxide base, right? Remember, this is the same thing as OH minus. Can I figure out the pH here? Not exactly. First of all, remember, pH is equal to negative log base 10 of H plus. So big thing, I don't have molar amounts of H plus. I have moles of OH minus. So I need to get molar amounts of OH minus, and then from that get amounts of H plus. I know you're like, what in the world? This is chemistry, y'all. Especially Gen Chem 2, man. You put it's like a huge remix, right? Kind of like Avengers Endgame. I'm sorry to all you people out there who love superhero movies. You're like, what's it called? Heresy. What, she doesn't even know what she's talking about. You know, when you have that movie where all the heroes shows up, that's what I'm trying to say. It seems like we're bringing in a lot of topics to solve this one simple problem. We are. We're bringing in stoichiometry. We're bringing in limiting reagent concept. We're bringing in acid and base. We're bringing in pH formula. We're bringing in pH and POH. We're bringing in a lot of things. That's what I meant by Avengers, y'all. Sorry, I am trying. We're bringing in a lot of concepts to solve one problem. Okay, that's what I meant. So we have to convert this moles back to molarity because the symbols we have here, these brackets mean big M, not MOL. So you can't put a MOL number in there and get it right. You get it wrong. Okay. So since we're not ready to use this here, I'm going to erase it. We're not even there. So how do I get the amount of sodium hydroxide to go from 0.004 moles to molarity? How do we get there? I have to take the moles present divided by the total volume. Okay, so what do we have again? Oh, we added 30 milliliter, but to what? What was the question saying? Oh, 50 milliliters. So we have 50 milliliter, we added 30 milliliters. So we are dealing with 80 milliliters, right? I'm trying to unfold it as we go along. So our total volume here is 80 milliliters. But remember, we cannot take moles divided by milliliter. It has to be in liters. So this will be 0.004 moles of OH, right? Divided by, what's 80 milliliters in liters? 80 milliliters. 1 liter divided by 1,000 milliliter. That's why the stuff from Gen Chem cannot be forgotten, y'all. You should see organic chem. It's like this and so much more. It's like Avengers all the time. Not really. It's a different kind of Avengers. It's like, what's the other one with DC? Justin Lee. Sorry, I was cheating for my husband. I'm sorry. I don't know this stuff, yo. I'm trying to be relevant. I'm just kidding. Right, right. In organic chemistry, you do the same thing too. When you're solving a problem, you bring in all the little stuff you learned before. So if you forget it, then it makes it harder for you, right? You don't want to forget it. So you want to study all the time. 80 divided by that. Okay, here I get 0.08 liters. 0.08 liters. Okay, I got my moles of OH left over. Divide by that. 0.004 divided by 0.08. So amount of base. Finally, I'm. You can tell I'm smiling. I made some progress. This is the molarity of the base, or the same thing as OH minus. So from here, I want to just find POH. POH is negative log base 10 of the OH minus concentration. If I have that, remember concentration means molar. I have the OH minus concentration, so that will be negative log base 10 of 0.005 molar. 0.05 molar. Yeah, I used the wrong kind of bracket, but you know what I mean, right? That's what goes in there. Okay, let me do this. Negative log base 10 of my answer. Oh, come on, calculator. Bear with me. Okay. Okay, so my calculator said this is going to be 1.30 for my POH. But remember, pH plus POH equal 14. Therefore, my pH is 14 minus 1.3. My pH is equal to 14 minus my answer. I hope this is right. After doing all this work, 12.677. Okay, so after I add 30 milliliters of acid, what happens? So they walk you through this. They get this part here. I walked you through the whole steps, everything in order. They did all that and they got 12.70. Okay, feel free to go over it. They kind of go over it slightly differently at some point, but feel free to go over this. Once again, you do have a recording, so you can rewind, right, and watch it until it sticks. For the second part, they said at equivalence point, the strong base has completely neutralized the strong acid. Fine. So when you reach equivalence point, what is the pH, right? At that point, if it's a strong acid, and a strong base, then the pH is going to be 7 like they got. Okay. Okay, since I finally done this, I know I went over by 30 minutes. I do apologize, but you guys have the recording so you can stop. So I can finally erase this here. I know it's the little things that excite me. And I'll say start here. So when we meet on Thursday, we will start here. And I'll focus only on KSP. Okay. I will try to do a recording for the lab that's due, is it to whatever on the 1st? Yeah. I'll try to do a recording for that one, just kind of give you an idea of how to work that one out because we've come to the point where I feel like we've covered enough that you want to go over the video and then work on the lab. Okay. Okay. This is all I have for today. I hope to see you on Thursday.
Thank you.
Okay, you're welcome. I'll talk to you later.